because the time is limited, so I just changed a small topic. For this one, I want to talk about the unified graph query planning, implementation, and optimization. First, let me thanks to my collaborators, Professor Timur Zhu and Professor Jeffrey, and Pan Yue and Yang Lingling, my current PhD student here, and Guo Xiangyang, my former PhD student graduate, and now in the postdoc in the University of New South Wales. This is my outline talk outline of my talk. We know the graph database is a new type of the NoSQL database and focusing on the query and storing the relation between different entities. And the main difference from the relation database that is the schema-less feature in the graph database. Because for the RDBMS relation database, we call it a schema first. That means that we should define the schema before loading the data. But for graph, especially for the RDF graph, because I working on the RDF graph, we call it the date-defined schema. That means that the more the schema feature, schema-less feature. The schema-less feature favors us to do the data integration from different sources, but also propose some of the challenge for the query planning, query optimization. This is what I want to talk about this today. We know for graph database we have two families. One is for RDF graph and the Sparkle query. One is for the property graph and different kinds of the property graph query language, such as GQL, Sabre, and many others. And thanks to the W3C committee for the RDF and the Sparkle, the many standards are well defined. But for the property graph, but now we know the GQL is a ISO standard for the property graph queries. We know that some of the difference between the RDF family and the property graph family. The first one is that for the property graph, we always represent the properties by key value tables associated with the vertex and the edge. But for RDF, we always represent the different for properties for the connection. We using the unified triple SPO subject predicate object to represent. There are many differences for the layout, the data model. I think this difference may affect the story layout, the query optimization, and evaluation. But today, I want to talk about common points. I mean, I want to talk common points between the two families of graph. The core query constructor for the Spark QA and GQ and Sabre and many others graph query language is the core query constructor is the same. That one is the conjunctive graph query. We also call it a subgraph matching. The other one is regular path query. So, so first one for the conjunctive graph query is that given a query graph, we found the subgraph query in the data graph that also morphism to this to the query graph. But for the regular path query, given a regular expression, we want to find a state of the node paths that connected by a path and the edge label along the path following recognized by this regular expression. This we call it the regular path query. For this one, we try to find some person follows or the indirect follows others, right? This is a very simple the regular path query. If we combine it together, we call it conjunctive regular path query. And it means that we replace one edge by the regular path that we call it conjunctive regular path query. This beyond the CIPQ, for CIPQ is for short that conjunctive regular path query. We also have the other graph constructor such as optional, union, aggregation, and top K, and many others. This is an example of show the optional query. That means that we found this age is optional age. We write down the two different query statements. One is for Sparkle, one is for Sabre, but they have the same meaning. This is the query graph here. In the ICDE 2002, there one paper proposed algebra that is originally defined for the streaming graph algebra, but it also works for the generated graph database. It proposes the different operators to incorporating the regular path query and the subgraph query. So this is the graph algebra. Okay, So we know, so for graph query evaluation, the overall the workflow, I think is similar to the traditional relational database. We also have the first part is plan enumerator. It means given a query, given a graph query, you should enumerate different kinds of the graph plans to represent uh, the the how to do the queries. But for each plan, we also need a cardinality and a cost estimator to estimate the cost for this plan. This is that is not the same with the traditional database RDM database. But the challenge here is how to represent the graph query. That is different from the traditional relational queries. And the second challenge here is that how to effectively and efficiently to estimate the cost and the cardinality for that. This is two main challenges here. So let me talk about the first issue. For this one, we show generate the graph query. For this one, we have a conjunctive query, we have a regular path query, we combine it together, we have a conjunctive regular path query. And beyond this, we also talk about some other constructs that are optional, union and aggregation and others. Okay, so this is a subgraph query. So a subgraph query, we also call it the conjunctive graph query. Given a query graph Q, and we want to find the matches of this query graph over the data graph G. That is, we call it the conjunctive query here. And for this one, we know in database committee, we have a lot of the research papers studying how to do the subgraph query papers. But from the perspective of the query planning, we have in our opinion, the two different kinds of the crowd plan evaluation first method for that. One is based on the binary join. Simply speaking, that given this query here, triangle shaped query and data graph here, we first find for each query age, we find the matching tables T1, T2, T3 logically, and then we and then we do the join, the binary join. We do the binary join over these three tables, T1 join, T2 join, T3. For example, we can use the Hashi join to do this, and following the left leaf join tree for that one. This is one query plan. And the other one, we can use the worst case optimal join. If using the graph language, it means that in each state, we extend one vertex at a time. For example, this is the worst case optimal join the plan. For worst case optimal join has some advantages. One advantage is that it can guarantee the number of intermediate results did not exist AGM bound as the worst case. But but even for that, we cannot just simply say the worst case optimal join is a binary join is better than binary join. In all the cases, we cannot say that because a worst case optimal join can only guarantee the performance in the worst case. So sometimes we may choose the worst case optimal join. Sometimes we choose another one. So we should have the cost estimation problem. These are two different plans for the subgraph query, and one paper and other paper follow that propose a series of papers propose the hybrid query plan. In the hybrid query plan, it means that in each join state, we choose a different join method. One for binary join, and the other is for the worst case optimal join. For this one, we in the first step we use the worst case optimal join, and finally we use binary join for that. So this is the hybrid query plan for the subgraph query. Okay, so let's talk about the second query construction, the regular path query. For regular path query, we given a regular expression R. We try to find a state of the node neighbors, a state of the node pairs. And this node pair are connected by a path, and the edge label along the path and satisfy some of the regular expressions. For this one, we try to follow find the people you follow directly and indirectly. You can write down this regular path query, and you can find this node pairs in this example. We also can give another example, the person like by people you follow, or the two examples for regular path query. For regular path query, we also have two different planning. The first one is based on a financial automata-based evaluation. Given a regular pass query, you can represent the regular expression by the financial automata, and following this automata, we can travel the data graph step by step, and the age, the following the age, the age labels, and these age labels can be recognized by the regular expressions. This we call it the first planning measure. Planning. The second one, we can use a rational algebra-based evaluation. We can extend for that by alpha operator. With alpha operator, we call it a fixed point. It means we can do the join or self-join over the intermediate results until no new rows are generated. We can extend the traditional rational algebra to support the regular path query. This is the second planning for the RPQ query. So we have the algebra. We have two different planning space. One is based on the automata. The other one is based on the rational algebra. So one paper in the Sigmod 2016, it proposed a hybrid query plan. That means we can substitute the two evaluations. And in this method, it allows the multiple automata for the subquery. And we materialize we materialize some of the intermediate results generated by the automata, and using the rational algebra to support the hybrid query plan query evaluation. This is the hybrid query plan for the RPQ query. Now, we talk about the complex one, the conjunctive regular path query. That means we combine the subground query and the regular path query together. For this one, this is the example here. And for this one, interesting that is we also have the two separate query plan space. One, we call it, similarly we can say, is based on binary join evaluation. It's something like the rational algebra-based method. You can just extend the query evaluation one age at a time. The only difference here is that for regular path query, we can using any RPQ query method I mentioned above to evaluate for that, and to join the intermediate results for other ones. So this is we call it the binary join based evaluation for the CRPQ query. For this method, the problem is reduced to the join ordering problem. So what ordering is over the ages should be negative for optimize the query planning, query optimization. The second one, we just simply say that it's based on worst case optimal join. For that one, it's something like the worst case optimal join for subgraph query problem is that for this planning problem is reduced to the variable ordering problem, because in each step we select a different variable at a time. And for this one, you can use the worst case optimal join for the RPQ without the clean closure. But for the someone with clean closure, you can use a fixed point operator to do that. It's similar to that. For the ongoing work, our ongoing work, we want to propose a unified plan space for all the CRPQ queries. We hope that query representation can represent the RPQ and subgraph matching by the same operators. This is our ongoing work. And beyond the CRPQ queries, I talk about we have some other constructors as the union, optional, top K, and the aggregation. For the top K, we have the one paper in this year's CICM. For the other constructor query, we have the CICM last year. For that one, we propose a evaluation tree. For this evaluation tree, you can see for each leaf node is a CRPQ, and the internode is the operator such as the aggregation, union, option, and other operators. And then we also propose some of the rewriting the technique. For example, for the union operation, union constructor, we propose the merge rewriting. We given a query, we try to rewrite the query to the optimizer one. And for the option, we also propose the injection rewriting and other rewriting the rulers to find the optimized query planning for that. Okay, I have talked about how to represent a complex graph query in a uniform query plan implementation. The next question is how to optimize for that. It means that given a query, how to find the optimized query planning for that. That I think this is a very big topic. I cannot cover all of them. Just given the first on one small topic for that. That is how to estimate the cardinality for that. For the cardinality problem, because we have different constructor, a conjunctive graph query, regular path query, and others, optional union, and different graph constructor. For the subgraph query, I think in the literature, in our committee, there are a lot of the paper for that. As I remember the yesterday afternoon session, we have some papers studying the estimating for the subqueries. So you can read a lot of paper for along this direction. But I think the main measures is something like the traditional ration database. Of course, there are also some of the using the graph GN measures to estimate for this subgraph query the kinetic estimations. For regular path query, there are also some of the papers, but only the for we on a very but the number of the papers studying this field is very small, and also there's one limitation for this existing works, that is they often assume that the maximum length of regular path. It assumes the maximum length of the regular path with the clean closure. I think in the general case is not true, right? So how to remove this assumption, I think is still an open problem for that. For the other graph constructors, such as aggregation, such as union, and optional, and the aggregation, and for different kinds of the other graph constructor, is something like the counterpart in the relational database system. So how to consider the graph structure in this setting, and how to optimize and efficiently to estimate such as the constructor, I think is also another challenge for that. Okay, finally, I just talk about advising our GSTOR project. GSTOR is designed by our group and also collaborate with Tamar Zoom people. And this is designed for the RDF graph database. And the first paper was published in the 2011. And in the for along more than 10 years, we always maintaining the project and in the GitHub. And we in current version, we using the uniform graph query representation in our query engine of the GSTOR. In the near future, because we in our talk, in my talk, I propose a uniform query plan. That uniform query planning can be represented the Spark query, can also be represented the Sabro query and the GQL query. So in the near future, we want to support both RDF and the property graph in the one system for that. This is the take-home message. The first one, I think the uniform graph query representation is very important because it lays the basis for the graph query evaluation and optimization. The second one is cardinality is the matter. Is another challenge for that because you should have the effective and efficient method for that. The third one I did not talk about, but I think is very important. I just talk about the query layer in the graph database. But you know, for the database system, we have different layers, query layer, story layer, and others, right? So interaction and independence between the query layer and the story layer should play a very important role in the query optimization. So I think this is also interesting topic. This is a reference I will talk about this talk. Thank you.
Any questions? So Xiang from UWaterloo here. Thank you, Professor Zhou, for this very interesting talk. I have actually two questions. The first one is about the cardinality estimation for regular path queries. So according to GQL standard, when you dealing with a regular path query, there are different semantics. There are walk semantics where you can have arbitrary repeated node and edges. There are trail semantics where no edge can be repeated. And there are acyclic semantic where no node can be repeated. And in practice, these different semantics can lead to vast different cardinality estimations. So I wonder what's your idea about cardinality estimation when user trying to use different semantics for regular path queries.
Okay. I think thank you for your question. Yeah, it's an interesting question. Because I just say that for this one it's an open question, so we have not clear answer for that. But I just give my opinion for that. I think the more challenging for the estimated for the RPQ regular path query estimation is that the clean closure operator. So for clean closure operator is no limitation, right? So I just say the limitation for existing measure is it has the upper bound assumption on the upper bound of the length. I think how to for the unlimited recursion is a challenge for that. We also see a study on for this problem. Yeah.
All right. Okay. Thanks for the.
Thank you. We should talk about offline.
Yeah. I have another question about your vision about unifying SPARQL and Cypher. So Amazon Neptune has a system that works for RDF.
Mm-hmm.
They allow either using Cypher or SPARQL to do that, but it's more like a different architecture. Like it's not a unified system in terms of using Cypher or SPARQL. So I wonder what's your vision of unifying these two? Is it like you are going to provide a system that at the grammar level you are going to convert Cypher to SPARQL and using a SPARQL processing engine, or the other direction? So what's your approach on this?
Okay, so I know your question. I thank you for your question, and this is also a big question for the in my opinion. Actually, in my talk, I think for the GStore system, yeah, we want to support both RDF and the public graph in one system. But honestly speaking, we can because it's easy to do in the query layer. I mean, the query layer is easy for them because I just say for the SPARQL query, for the for Cypher and the GQ, we can use one unified query planning for represent the query plan. But it's little difficult in the store layer because the layout of the date is different. So we can maximize the common reuse some common part of the story, but I think it's different. We cannot use one story layout, story data structure for both the public graph and the ADI graph. I see it's challenging for that. So in our GStore system so far, we unify the query layer. For the story layer, it's still the separate.
I see. Okay. Thank you very much.
Thank you, Peter.
May not have understood it well or paid enough attention. Sorry. So, but apologies for that. But so, what are your plans with respect to GQL? So, because this is a SPARQL system, if I understand correctly. So, can you comment on that? And do you think that that would, for instance, I mean, moving from a SPARQL to property graphs would potentially also impact the query planning or also the cardinality estimates, because then you would have to deal with more structured data, because you would have some stronger notion of schema in property graphs than you would have in SPARQL, in RDF.
Yeah, I think Peter mentioned is very important. For the property graph, we always have the schema, right? But for the RDF, maybe
not always. I mean, there are systems that have the schema and some systems that don't.
Yeah, I think if we have some schema, something like the schema, we can optimize the data organization.
Yeah,
especially for the story layer.
Okay, and how do you do that?
So I just asked the question. My answer for the last question is that for the story layer, we for the RDF and the property graph, we separated.
Yeah.
There are two. There are
Different
separated,
storage layers.
Sorry, yeah. For the query plan, we
Yeah.
can using the uniform query engine.
Okay.
Yeah.
Okay. So, but the storage will deliver different statistics
Yes.
for the
Of
property
course.
graph
Of course.
than
Of course.
it will deliver for the RDF.
Yes. Yes. Of course.
Oh, okay. And what is the exact status of kind of the GQL support? So can you comment on this?
You mean
So what kind of query language do you? What is the current state of the query language for property graph?
You mean the benchmark?
The functionality.
Finish. Sorry.
Functionality. So what features do you support?
For the property graph,
Yeah.
I think we're using LDBC the queries.
Mm-hmm. Cipher.
So
you do you have support? Do you have plans for GQL?
Of course, we should. We hope for that because we have the one project that requires the Cipher. So we first implement Cipher first.
Okay.
I think there's some difference, but the main comments is much larger. For the Cipher, for the regular path, it's only the label constraint reachability query. It's only for the regular clean closure. But in GQL, regular path is fully supported. So that is the difference. There's some of the difference.
Okay, well.
We try to support the GQL in the future. Yeah.
Okay. Well, success. Keep us posted.
Yeah. Thank you.